Okay, let's get started. And okay, so today we will finish the multipolar approximation that we worked on. So last time mostly it was about like why it works, some justification, and then some procedure like what you can do in order to do the multicolor approximation. And then for today, we mostly will talk about the posterior predictive, like how you can make prediction, and then how posterior predictive can be helpful as a way to evaluate whether your model is a good model or not. Okay? So we'll do that. And then before we start, let me see. If you haven't done the self-intro post, please do that as soon as possible. Also, yesterday I sent out an email about some of the, that I think, identifiable project interest. I made a post on Moodle, and I think I listed maybe like eight different topics that I noticed that may be common, and some of them are more popular than the other ones. For example, like econs, we have a lot of double majors, but there are also other topics like biostatistics, or very specifically, say, healthcare, and I think we actually got 3 students interested in those, and then there are others. Give me a second. And there are some topics maybe just one person is interested, but still, like I just want to post them over there so you can start thinking and then start connecting to the others. And also in the same post, I also make some other notes about, because people talked about what kind of courses they have taken before, and then what is the relationship between what they have done before or what it's doing related to what we teach right now. So I also post 4 different items at the end under the title of other info. So for example, like Markov chains, I think we have 2 students actually took a class on that before, and then that might become helpful. So I would really appreciate if those of you who had experience before can make connection to what we are doing, we will be doing soon. And et cetera, et cetera. And also like page use data cam, which is like I guess it's a website, but it's an online course for programming online to learn R. So that might be a good resources out there. So again, on Moodle, we have separate section on just R. And I started with like 2 discussion big discussion topics. One is any questions about R that you are having in terms of doing homework or anything else, but also your favorite R resources to share. So please start populate all of those as you see appropriate. And okay, so I think that's mostly what I would like to talk about at the beginning. And also just to encourage like collaboration across different like among different students, especially like across campuses if we can. I thought about, because I know homework too, some of you spend a lot of time doing it, and there's some common questions here and there. We'll see at the end of this, towards the end of today's lecture, if we get time to talk about them a little bit more, but even if we don't, I still want to want all of you to like team up to work on, not work on, but like work on together as well, like 3.3, the tumor counts example, like homework question about the gamma plus count. So after class today, I will send out a team assignment, but it's really just names and then emails, and then you will still do it. I mean, it's still part of the homework to submission. But at the beginning of Monday, the coming Monday lecture, I just want like, there's 3 parts of this question. I would like people to like maybe make some comments and then show up what they have done. Maybe just take the first 10 minutes of the next lecture to talk about that particular problem. But you should still submit that as part of your homework. But hopefully, I mean, I know some of you already start working on problems together, but still, if there's any way that we can incorporate the other students from the remote campuses, or just make people within our class talk to each other outside the usual circle that you already talk to, let's try to see if that can be a way to facilitate that. Okay, so after class today, I will send an email so you'll see what I need. But in particular, just do 3.3, and then there's 3 parts about it. You probably have done that already. You might have some similar struggles here and there. So just a way to start talking about things. All right. Okay. So there's that. So if we finish the lecture early, we can talk about. I would take questions from the homework so we can talk about it. All right. So let me just show you the particular stuff that I would like to talk about, and then and then we do some R practice with it. Okay, so last time we talked about like the introduction of this multi-color approximation, and then we talked about some procedures, how you can do it, and we extend that into functions of theta. Okay, like odds ratio, and then also other kinds. And in particular, we talked about different critical intervals. Some of them are invariant, some of them are not. So make sure that you know in what situation you're going to use what. And then the most, like I wouldn't say most, but a lot of people actually pay attention to the posterior predictive distributions. So first of all, making prediction can help us learn about future events, and making prediction is a key element of a lot of statistical learning. So this will be one motivation of why we're doing it. So we're going to see examples. But most importantly here for this particular chapter, I want you to start thinking about, okay, if I can make predictions either out of the prior distribution or out of the posterior distribution, I can kind of check if the new generated data can be very similar to the data that I see, right? So that can be a way, a very rough way, like not really like a systematic way, but still it can be a way to check if the model that I set up or if the way that I'm estimating the model is really helping me to understand the data. So we're going to talk a little bit about that and do some practice with it in R to see how you can do posterior predictive checks. Okay, so you see that it's PPC, yeah, posterior predictive checks, yeah. All right, so let's think about this context a little bit before doing the actual predictive. Here, I actually want to just take the time to introduce you the exponential model. This again, going to be requiring the gamma distribution, which we're going to spend a few minutes on as well, because that appears in the homework. Maybe you don't know much about it, so hopefully through this you can have some better understanding. So exponential distribution as a statistical model actually have been used to model interarrival times. For example, volcano eruptions, like the time lapse between two events, say volcano eruptions, traffic accidents. So let me just introduce the particular context we're working on. So suppose we are modeling the time between accidents using exponential distribution. So exponential distribution has only one parameter, which is the rate, and we use beta to represent it. So suppose for a particular location, we collect 10 times, like 10 data points here. So here the y is just telling you in terms of minutes, what are the not interarrival, like the time lapse between different accidents. So we're looking at 10 different times over here. Okay, so this is the context that we're going to work on, and you will see that how, like, let's explore in the Bayesian paradigm how we're going to use a conjugate, in particular conjugate prior to conjugate is to do this. Yes, the data, so 1.5, 15, 60.3, all of this are the time, like the time lapses. Yeah. All right, so first of all, let's just pause and then do some practice to make sure that we can verify this is a conjugate case. So this is a one parameter model that people use a lot as well. In particular, it's a gamma prior for exponential model. Okay, so I put the gamma prior, like the density of gamma, and then the density of the exponential distribution over here. And I would like to ask you to try to derive what will be the posterior. And then after this, I'm going to introduce more about this gamma distribution. So right now, take it for what you know. And so beta, which is the rate, is gamma AB. And then the density of beta is in this form, or in this form. And then down here, I wrote the y. And notice that over here, you have, right, so you're gonna have y, so each yi is IID exponential with parameter beta. So this will be the density, and make sure that now you have n yi, okay? So you can also write y1 until yn to be IID exponential. Okay, so because now we're considering multiple data points, so make sure that you're expressing the joint correctly. You're not only doing for one data point, okay, you're doing for n. So try that. Let's spend a few minutes on this, maybe just 2, and then make sure that we're now familiar with how to derive a posterior from the prior and the likelihood, as well as getting practice at how you can identify the kernel efficiently. In this case, it's a conjugate, so you know that the posterior will be a gamma again. But of course, we need to identify what is the new A and what is the new B for the gamma distribution. Okay. So if you've done it, I put up the answer on the slide. You can check if you get the new A and new B correct. Agreed? Okay. So you notice that because the random parameter here is this beta, so the kernel will be beta raised to some power, and then the exponent, some negative thing multiplied with beta. Okay, so that means, and then also over here you see that this is beta raised to the power of 1, and this is an exponent negative yi beta. Okay, but make sure that you know y1 to yn given beta is the joint, okay, of all of the yi. So not only express just one piece of yi, but n pieces of them, and then you product them together. And once you collect the terms, you'll realize that in the kernel, it's going to be beta raised to the power of a plus m minus 1. And then in the exponent, it's negative b plus the sum of yi times beta. And then that helps you to recognize the kernel. Okay. All right, so if you've done it, this will be the gamma that we're working with. And any questions? Or anything that's not the same one? Okay, all right. If no question, we would take this as what we know for now. And this is a conjugate case. You start with the gamma for the rate, and then you combine with exponential model, and then it's going to be conjugate, so you're going to come with the gamma posterior for this particular beta. All right, so we'll keep in mind this is the conjugate model that we're going to work on. And the question, now we're concerned with, the first one is how to predict the waiting times for the next accident. Okay, so predictive, but also of it is what about how to evaluate whether the exponential model is adequate or not. Okay, so this will be the two main questions that we're trying to from this lecture. Okay, prediction, how to for next extent. So maybe I shouldn't use waiting time. It's like the time for the time lapse for the next extent. And the second one will be, okay, if I can actually generate new data, if I can generate a lot of new data from the posterior distribution, and I'm going to compare that to the data set that I have, then maybe that can help me to evaluate whether my data model, which is the exponential, is a good one or not. Okay, but in order to, right, there's always a minus one. Yeah. Okay. All right. Okay. So before we go there, just a little bit more information about this gamma distribution. In particular, I think for homework, the question that I will ask you to present a little bit on Monday is 3.3. Over there, that's a conjugate of gamma Poisson, okay, and then gamma posterior. Okay, but let's talk about this gamma distribution a little bit more. In particular, in this class, we'll focus one way to parameterize it. So first of all, gamma, if theta follows a gamma distribution of parameters A and B, so now just like keep in mind we're doing A, B over here. And then for the parameterization that we're going to use in this class, if you have gamma AB, the mean will be A over B, and the variance is A over B squared, and the density is in this particular form. Okay, so this will be the only one that we're going to use. I know some of you have taken, especially in econ classes, I think they use a different way to parameterize the particular gamma distribution. So this, I think maybe this one, the second one, not in red, that econ people will use more. But in our class, we will use A as the shape parameter and B as the rate parameter. Okay, and if we define A and B to be shape and rate, then the density is in this particular form. Okay, so this will be the one that we stick to, and in R as well. So if you actually have started doing some coding with the gamma distribution, you will realize that in R you can do it two ways as well, just because there are two common parameterizations of this particular distribution. So for both in class as well as in R, we're going to use this shape and rate. Okay, so I will highlight it later once we get to the left part. So if you have a gamma distribution AB, shape A, rate B, then this will be your density. Okay, there's some, yeah, so first of all, theta needs to be larger than 0. Both A and B are positive as well. And the mode can exist, depends on the value of A. All right, so some plots, so some examples of gamma distribution using the, okay, so it's gamma AB, shape A, and rate B. Okay, so that's what appears in the legend over here as well. So different gamma distributions. You notice that all of them are positive. The shapes change a lot. And but again, I think it would take some practice for us to get a sense of what gamma distribution looks like, especially which one would be more useful in what situation. So this just a plot to give you some ideas of what different shapes of gamma distributions can be. But overall, this is used to model the rate in the exponential distribution. Okay, all right, so based on what we know so far, if we want to do posterior predictive, meaning that we're predicting, making prediction, and we are using again the notation of this Y star to represent a new draw, okay, a prediction. So in class, when we talked about the beta binomial model, I think we used something similar, remember? And then we did the derivation, and we realized that in the end, it's going to be a Bernoulli for each new draw. Okay, so here, what about for the exponential and the gamma exponential example? So if you write it, notice that right now we haven't plugged in any of the particular density for the beta and for the Y yet, but this is true if you have one parameter model. Okay, so in order to make a prediction of Y star given given the data y, you are doing the joint of the prediction plus 2, and then the parameter given the data, and then you just integrate out this particular parameter, and then that will give you y star given y. Okay, and the natural next step, we did that for the binomial beta binomial case as well, is you introduce, because you already have the distribution of the posterior, so the joint of y star and beta given y can be written as the conditional of y star given beta and y multiplies with the posterior. Okay, so this is just a quick review again. So notice that I'm not proceeding with any of the hard calculus over here. I put the slides at the end if you're interested in how you can actually get the analytic solution, but that's not the focus for our class this time. So let's look at how you can make posterior predictive based on the Monte Carlo method that we have learned. Okay, so what we're gonna do, if you see, if you try to do prediction from a gamma exponential model, what we're gonna do is, if you already estimate, so this we know is a gamma, right? We know that because gamma exponential is a conjugate case, so we know the posterior is going to be a gamma, and we have the two hyperparameters, the shape and the rate for it. So if we know that distribution already, we can actually draw a new beta. We use beta upper script I over here. You draw one new beta, and you notice that I is from 1 to capital S. So capital S is the number of draws that you make in the Monte Carlo approximation, right? So the first step is you're going to draw a beta I from its posterior. And then the second step is, because you know that, so what is this? The data model is exponential, as what we assume in the beginning, right? So if you have a draw, which is from step 1, you have a draw of beta I, and then just given that draw, you can make a new prediction of the y star. Okay, so this is the procedure. Okay, let me just explain again. So right now, first of all, I have the posterior of beta given y to be a gamma. Okay, and I know I just use A1 and A2 over here, A1 and B1 to represent the two hyperparameters, and I know this. Okay, so because I have that, I can actually draw. So over here, I use beta I. Draw in R, it's going to be R gamma, random draw of gamma distribution. You can tell that I'm going to draw one of it, right? And then the shape parameter to be A1, and the rate parameter to be B1. Okay, so this will be the first step. Once you do that, imagine you have a draw of this beta. You have a particular value that you draw out of this gamma distribution. And we know that given beta, the data are going to follow exponential distribution, right? So the second step, let me erase this part. So the second step is, okay, now I have a gamma draw, now I have a beta draw. I'm actually just going to draw a new data point from the exponential sampling model that we have. Okay, so what we have is, okay, the second step is we're going to draw y star given the draw that I had from the previous step, and I know that it is exponential distribution with beta I. Okay, so in R, you're going to get a new draw y star to be a R expo, and then with the beta I that you have. Okay, so procedure-wise, this is what you're doing. Okay, so and then in the end, when you're trying to like summarize the y star, because you can draw actually not just one of them, you can draw many of them, and then there's certain guarantee that the density or like the distribution of all of the drawn y's that you're getting is a approximation to the actual y star. Yes. Yes. Okay. Yeah. Yeah, I will give the example soon, but right now I just want to talk about the procedure. All right, so let's pause a little bit. So based on the procedure, what we're getting, we're gonna get a sequence of beta I, right? Or like sequence of beta. So what we're having is we're gonna have beta 1, beta 2, and beta capital S, right? Because that's the number of draws that we're making. And at the same time, we're having Y star 1, right? Y star 2, and Y star S. Okay? So in the procedure, like once we have done this predictive, posterior predictive generation, you're gonna get set of this and set of this, okay? And in particular, each of this is a pair, right? Because for example, for the first pair, you generate the beta first from its posterior, and then you generate the Y star. And then for the second beta, you're doing like a random draw from the posterior for beta, and then you do a second draw, et cetera, et cetera. So all of this, you can consider them as a pair. And if you think about the pair, this is what we're trying to do over here. Okay? You can imagine that like the pair of beta and the Y star that we're getting from this procedure is trying to get that distribution. And that's what we're trying to do, right? Once you integrate out beta, that's what you can get. So each of the pair, eventually then all together, is trying to approximate this particular distribution. Okay? And once you've done it once, or like have done it once, I think you will see like it's actually a very straightforward procedure. But overall, I just want to show you that, first of all of these betas are independent. Okay? And you know that because we're drawing it from this beta, from this gamma distribution, and use R gamma in R. Okay? And because all of the beta is independent, all of the Y star is going to be independent, right? Because you generate independent beta I, and then from each of the beta I's, you're going to independently generate a new Y star. Okay? I want to point out the independent case, like the statement of the independence here, because remember we're doing multi-color approximation. Okay, when we're doing multi-color approximation, we had the assumption at the beginning saying that, okay, if you want to have a good approximation to the truth, you need to have independent draws. Okay, so over here you see that we're drawing for a capital S number of draws, and that's the multi-color sample size that we talked about before. And last time we were saying that, oh, you can make it 10,000, you can make it 5,000. The larger that you make it, the more computation power that you will need. So you will try to strike a balance between how accurate that you want and how much time that you have for the program to run. So, so everything now is still under the topic of multi-color approximation. So that's why it is very important to make sure that we're doing independent draws. Okay. Yeah. And from there, like last time, Nick actually stayed after class to ask about like multi-color and then Markov chain multi-color. So we'll talk about that more, of course, once we get there. But I just like this, like a plug-in over here. So for multi-color, they're all independent, right? But once you start doing Markov chain, you have learned about the term before, like stochastic process, all of that, you see that things are not independent anymore. Okay, your current is dependent on the previous, or the previous one, or the previous two, et cetera, et cetera. You can have so many different ways that can happen. So in the end, the computation methods that we can use as the Markov chain multicolor, MCMC, is trying to draw like a lot of parameters iteratively, but in the end, we still need to use multicolor, which means that we need to get rid of the dependence among the draws. Okay, so we will get there once, yeah, we will talk about it in detail once we get it. But I just want to point out that here, because it's just multicolor approximation, we're doing independent draws. If they're not independent, the approximation is not good. Okay, awesome. So just a little bit before we move on. So here, the gamma, let's see. Okay, so for now, we're using a default prior. We'll talk about this maybe in another context, but for now, for the gamma exponential, the default prior for this beta is 1 over gamma, 1 over beta. and it's a gamma 0, 0. Okay, just so you know, it's gamma 0, 0, so that's the prior that we're going to use. So because A is 0, B is 0, so the posterior will just become n and sum of y, okay, based on what we did before. So for this particular traffic accident example, n is 10, n is 10, and then the sum of y is 336 from the data that I showed before. There are 10 data points, and the sum of them is 360. Okay. All right. So that means the posterior is a gamma 10 336, and then we still know that the data model is exponential of this beta. Okay. All right. So this is background, and let's see how you can do it. So earlier we're talking about, okay, first of all, I'm going to draw beta. Okay. And then second, I'm going to have the new data draws. Okay. This from the posterior. And this is from the data model. Okay. So you notice that the data model is the same as before. That's the basic assumption that we have. Okay, so make sure that you know what they are. So in terms of code, it's actually very straightforward. So I initialize, I didn't even initialize it, I just named beta to be the vector of storing s equals to 10,000. So here I'm doing R gamma, so R is random draws in R, right? So you do R gamma, you tell R how many draws that you want to make, you tell R what is the shape parameter, and you tell R what is the rate parameter. Okay, so after this one, what I get? I will get a vector of 10,000 independent gamma draws from gamma 10 336. Okay. Okay, and the second step, I name it as new y, as new star, like a y star, but just name wise, I just use new y over here. And then you see that I'm using REXP. Here, the R, again, is random draws, and EXP is the function to write to get the exponential draw. Okay, and then again, I'm doing 10,000, 10,000, and I'm remember exponential distribution has only one parameter, that's the beta. So I just get the beta over there. Okay, so this again tells you like another feature of computation in R that they're doing it in terms of the vector. Okay, if I have a vector of 10,000 values of beta, then I can just on top of that, I do REXP. It's the same length, and then I just fit in. So over here, this is the vector of 10,000 betas, right? So R will know that I'm drawing it accordingly, one-to-one correspondence to the new y. So new y here is vector of 10,000 y stars. Okay, yeah. Make sense? So yeah, don't worry. So over here, once you do this, they're all independent draws. So this guarantees that we're doing independent draws over here. Okay. So so this means now, okay, we have 10,000 new predictions. Okay. So if you have that, say, if I'm curious about the question, okay, what will be the probability, or what will be the probability that the next accident will happen more than 30 minutes later, if I have a question like that? Because now I have 10,000 different Y stars, which are the times, like time lapses between accidents, right? So if I have 10,000 of them already, and if I'm curious about the question more than 30 minutes, then I can actually return it using this mean and then a logical operator over here, right? So this new y has 10,000, a vector of 10,000 values, and then I'm checking if it, how many of them, or whether, sorry, not how many of them. Over here is each of them, whether each of them is larger than 30, and then that will be binary, right? 0, 1. So if I return the mean, they're going to give me the probability in some sense. In here, we define it to be the posterior predictor probability that the y star are going to be larger than 30, is about 43%. Okay, so using this prediction, so this is just one demonstration of why you can summarize this. So if you're curious about the question, okay, what is the probability that I'm gonna have more than 30 minutes time before the next accident gonna happen, then you can do this. But of course, you can do something else, like, okay, what if I want to know the probability that between the next, from now on, between 10 and 20 minutes, what is probably that an accident gonna happen, then I can actually also return something in a similar manner. Okay, so it really depends on the question you're interested in. So here I just gave you some examples. You can do this mean with the logical operator, or you can also return the quantile, which is the middle 95% credible interval of the waiting time. Sorry, the word I'm using is not really good. It's not happen. Time left. So here the probability the single credible interval is 9 to 152. So that means for 95% probability that time left between now and the next event will be about to 152. Based on this stability, and that is stability. So this is something else we can do, and you can actually summarize in so many times. A lot of the questions that we work on, really apply this syntax, even though you know, like you first of all, sometimes you direct something and make everything work going on. And all of the last question I was saying, how do you answer the question? And again, when you start your own project or thinking about how you can apply the method into something you're interested in, and also think creatively or like think in the context of the person you want to answer. Okay. So for the majority of the class, the course itself, we're going to learn about those methods and then like why they work, how they work, and how we can implement them. But in the end, if you want to make it work for your own project, you need to be the person asking those questions, or you need to be the person who's talking to others who are interested in this type of questions to come up with useful and meaningful ways to summarize the results that they have. Okay. So the posterior predictor is just one example that you can do. And then just even within it, they have so many different things that you can do. So here I just gave you some examples of what you should be thinking as what you can do. Okay, so the last topic for here is posterior predictor model checks. Remember, so it's actually short as PDN. So here is posterior predictor model checks. So here we're doing posterior predictor, not anymore we're interested in what the prediction will look like. We're interested in, okay, what the prediction that I can get, and that helps us to evaluate how good the model is. Okay. Still bad? Give me a second. Sorry about that. Is it better now? Okay, yes. So it is better now? Okay, okay. Thank you, because other people need to rely on the recording, so thank you. Okay, so we were talking about, okay, so earlier we talked about posterior predictions, how that can help us make predictions, but now we're interested in, with the predictive power, like the power that we can do the predictions, can we actually check how good the model is? So the general idea is, okay, now we can make a lot of predictions of new data points, right? New data points, and then if you generate a lot of them, and then if you compare what you generate, because you're generating new data, and if you can compare, if you think about special statistics, say like the mean or the variance or like the 53rd quantile, et cetera, any kind of interest, any kind of statistics they're interested in, if you generate a lot of new data and then you summarize those data, and if you can compare to what you have seen for that particular, the same statistic, what you have seen in the original data, that can actually give you some measure of how good your model is doing. Because the new data that you generate is based on the model that you estimate, right? So the more, once you have the access to generate a lot of new data points or a set of new data points, and if you compare to what you have seen in the data, if they're very different from each other, that might tell you that, okay, maybe the model that you did is not right. Maybe the model itself is not good, or maybe like the prior that you put is not good, et cetera, et cetera. There's so many possibilities that things can go wrong. So, so that's one thing. And also, if you did see that, okay, my observed data, the sample that I have, is not that different from all of the predictions that I can make. So maybe it's telling me, okay, maybe my model is doing an okay job. So that would be like the other possibilities. But again, note here, posterior. So we call all of this as posterior predictive model checks. Those checks actually cannot validate that your model is correct, only if you can see that the checks are telling, like pretty much you can only say that if the model is not describing the data well. Okay, so this is, I mean, not a rigorous way to check, but still, people would like to try it just to make sure that the basic criteria is being satisfied. Okay, so procedure-wise, this is what you're gonna do. So I list them into this 5 bullet points. The first one is you specify a test statistic, so we use T, that is useful for model checking. For example, like means, variance, functions, or residuals, et cetera, et cetera. So maybe let's just keep using mean as a working example. The second step is you generate a large number of new data sets from the posterior predictive distribution, which we talked about previously. Okay, and notice that you are generating a large number of new data sets. Okay, it's not just new data anymore. So for example, if in the original data I have 100 observations, then what I'm doing is you're gonna generate S sets of 100 observations. Okay, because each time when you generate the posterior predictive, you want to mimic what you have in the original. So if you have the original, say, to be 100, then every time if I generate a new data set, I should generate 100 observations and then summarize its mean, the variance, standard deviation, etc., whichever you prefer. And then here, generate a large number of that is talking about, say, if capital S is 10,000. So it's actually going to be a loop. Like if you think about writing in R, you're going to write a loop that you're generating 10,000 different sets of new data sets. And each set has 100 observations. Okay, so this is different from the previous posterior predictive, right? Because for the posterior prediction, you just want to make prediction for the new time or for the next occurrences, et cetera, et cetera. But here we're doing posterior predictive checks. And then the key idea is that you start with the statistic, like the mean, that can help you to check the model, whether the model is good or not. And then you are doing this check, we are returning the mean for so many different data sets, newly generated data sets, and then you're comparing your observed to the new sets of means that you can get, right? So for each new data set, you're generating like 100 observations, and then among that 100, you're going to summarize the mean, right? And you're doing the whole process for capital S number of times. Okay, so that's the difference between between what we are doing now and what we just did with the prediction. All right, so that's number 2. Number 3, you're going to compute the mean in each of the simulated data set. Okay, and then number 4 is, okay, so you notice that we're returning, this is pretty standard practice, but I want to explain a little bit more. So this is the truth, right? We have the true data set Y, and then TY will just be the statistic from that true, like the only data set that we have, the sample that we have. So in this case, will be the sample mean. Okay, so we're returning the probability of, in the predictive samples, say capital S number of them, the percentage of 10,000 newly generated data sets, the percentage of how many of them actually going to have larger than the true mean, or 1 minus that. Okay, so the problem is, if either of this is very small, this is telling you that the model is not doing a good job. Yeah, let me just like pause this for a little bit. You compute the probability of how, like, out of the 10,000 newly generated samples, you calculate the mean, and out of those 10,000 means, you are returning the probability of the 10,000 means going to be larger than the truth, or 1 minus that probability. So if you imagine, okay, imagine I'm doing 10,000 draws, right? If I can plot them, say I plot the mean, each of the sample mean from the posterior whatever, and then I'm going to compare. So all of, say, this histogram is trying to summarize histogram of T Y star, right? And then I'm going to compare this to the truth. So the truth is TY. Okay, so let me ask you, if my truth is here, is it good? Good for the model, I mean? If the truth is somewhat, I mean, not that different from the majority, which is going to tell us that, okay, the model is actually doing an okay job, right? And then what if the truth is here? Then that's probably not good, right? Because we're generating the new sets of data based on the posterior predictive distribution. And then every time we return the mean, I'll realize that, okay, if it's the blue one, then meaning that the truth is not that far away from the majority, while for the yellow one, it's very far away from the majority. Okay, so just one more second. So this Q probability is trying to help us to capture anything like the yellow ones over here. Yes, Eli?
So when we do this, are we evaluating the effectiveness of only our posterior predictive model, or also just our posterior distribution altogether?
Good point. So Eli's question is, when we're doing this checks, is it checking just the posterior predictive distribution, or is checking the posterior altogether? What do you guys think? Posterior predictive distribution is actually based on the posterior distribution of the parameter, right? Think about earlier the procedure that we talked about, how you're going to generate all of this new waiting times of accidents, for example. You generate beta from its gamma posterior, and then based on the model, which is exponential model, you generate new waiting times. Okay, so the posterior predictive is actually a combination of a lot of things together, and that, so I guess a similar question to ask is, okay, now if things are not looking good, which part went wrong, right? And then again, because the posterior predictive has so many factors in it, it might be a really hard question to answer, right? It might be the prior that you did is bad, or maybe you shouldn't use exponential distribution, or like your like the estimation procedure is not really good, so you're not doing a good job. So there can be many different possibilities out there, but overall, if in the end the posterior predictive checks are telling you that the model is not good, when we say the model is not good, it's pretty much talking about the entire thing. Okay, it starts with the prior specification and also the model, like the data model that you put, and then until the end goes to the posterior predictive. So pretty much in the end, the outcome that you see is from the posterior predictive distribution, but that comes from all of the previous factors altogether. Okay, all right, great question. Okay, so this is just a general procedure, and then let me just show you how you can do it for the particular travel, like traffic accident example. So remember back then, you have 10 data points, remember, in the original data? So now I'm actually specifying a matrix to store all of this newly generated data. So I initialize the matrix, and I'm doing 1,000 different new data sets. So I just have 1,000 rows and then 10 columns. Okay, and then I write a loop. In the loop, I will first generate the new beta from its gamma distribution. And then I'm going to generate new y's. Okay, again, here, pay attention that you have one common beta, and then for each of the beta, you're doing 10 draws from the exponential, because that's what you have from the original data. So once you complete this loop, you will have a 1,000 by 10 matrix storing all of those newly generated data. Okay, so each row is a new data set. Okay, so if you're trying to do the posterior predictive checks with the mean, that means the next step that you will do will be, okay, I will just summarize each of the mean and then plot them and then try to check whether my original mean, remember the original mean, the sum of yi is 336. So the sample mean will be 33.6. And then I will plot that to see how likely or how unlikely that is to all of the draws that I have over here. Okay? So this is just a technical detail how you're going to do it. And I prefer specifying or initializing a new matrix at the beginning, but you can always do something else, depends on which you feel more comfortable with are. But this will be one way to do it if you want to do the posterior predictive checks. So a few things I did over here. I looked at the mean and the standard deviation ratio. I also looked at, so these are all of the statistics, right? So first one, I looked at the mean of the standard deviation. The second one looks at the max. The third one looks at the mean. And then this will be the code that you're going to use to do it. So in this case, you can plot them, but also remember we're talking about you can actually return the probability of larger than the truth. So over here, I got 3 probabilities. Each of them is for a specific statistic over here. They're not that extreme, right? They're all kind of like in the middle, because all of this is comparing to the truth against what you can have from each of the data sets. Okay, so with like 0.68, 0.38, 0.64, I guess it's not saying that it's a bad model that I'm doing. But if you see something like 0.01 or I don't know, like under, I think anything under 0.1 may be an indicator that, okay, it's not really doing a good job because your true mean is so far away from all of the newly data sets that you can generate. Okay, all right, I think, right, so I think these are actually just, yeah, all of the procedures. So the next 2 slides I won't talk about in class, it's just the analytic solution to the particular predictive distribution for the exponential gamma if you want. And you can read that for fun later. But for the rest of today, if you brought your laptop, please bring it out. And on Moodle, I actually I already posted the code called, I think it's R script called MC approximation to do all of the R code that we covered so like in this entire lecture. Okay, so if you want to play with that, feel free. But I did prepare some kind of exercise that we can do as a class if you want. And let's see how fast we can move with the material. If not, I can also make it as part of what you should talk about as a team on Monday at the beginning, in addition to the exercise from the homework question. Okay? So you can, right? So okay, so on Moodle, if you go to Moodle on the page, there's R script called MC approximation. That is for all of the code appear in the slides. Okay, so if you open it, you will see the sample code over there. But what I'm just giving out right now is something different. So feel free, you can work on this, or you can work, you can go through the MC approximation, that R script, to see what you can do with multi-color approximation that we learned so far. But the material I'm giving out and grant is actually also on Moodle. It's called Lab 2 under the same header, and that's like an exercise of generating posterior predictive distributions from 2 different approaches. I would like you to try them and to verify whether they come to the same conclusion. Okay, yes. Mm-hmm. Oh yeah, good point. What do you think?
I don't understand.
Okay, so the model, okay, let me just answer that in the class. Okay, so Serenity asked a really good question over here. I guess I went really fast. So why it is 1, not 10? Remember earlier when we're generating new samples of Y, we're like doing, like 10,000 beta, and then for each of the beta we're generating a new Y, right? Here, pay special attention, because what was the assumption in the data model? The data model is saying that all of the IID follows the same exponential. Okay, so when you're generating a new data set which contains 10 observations, you should generate from the same data. So that's why in the loop, so what is this? This is I'm doing the new, like 1,000 data sets. So in the loop, for each of the data set, I only have 1 beta, right? So this is 1, but here is 10. This one is only getting 1 beta, but here is from 1 beta, I got 10 observations. Okay, so very subtle, good point. I guess I missed it when I was describing the procedure, but definitely think about it. It's a very important point. And you will see that between, just on this particular point, you will see that the regular posterior prediction that we do and the posterior predictive checks that we do, they work in a very different fashion. Okay. All right, so the MC approximation, that R script contains all of the examples in class, and the extra, right, yeah. And then the handout that I just gave, you can think about it, you can work in pairs, and let's see how fast we can move. If we still need some extra time, I would just make this as part of what you should talk about on Monday as a team.
Yeah. I would expect it to be like 11 point something to 37 divided by 20, right? But then I get very off.
Oh yeah, because this, okay. The mean, you have to generate a lot of gammas and then take the mean. You're using D gamma over here. D is the density, so you're not getting draw.
Okay, so this doesn't take distribution.
But what you want, I thought you want the mean of the mean of the gamma distribution, right? So if you do R, and you probably don't need x2 over here. You're just gonna do like, yeah, exactly. Yeah, and then round up, yeah.
Okay, and I'll also
you don't have to do the plot.
I just like to do it for myself.
What do you mean over here?
Like this is how I did the D, the density. Does that make sense?
Yeah, I think that's fine. But can you just run like the gam really quick?
Oh yeah.
Yeah, on the top, and then return the mean, because I want to see if that solves the problem that you have.
Okay.
Yeah, run this and then run the next one. Yeah. Right?
Oh, perfect.
Yeah. Okay. Makes sense?
So when to do the random?
Right. So So if you know what the distribution is, like this is the gamma, and you know that gamma mean is A over B, then you can actually use the formula directly, right? Doing the random draw and then take the mean is just one way to verify, and that's multi-color approximation.
Okay.
Exactly what you did.
Okay. And so do the same thing like Q gamma would be the
quantile. Yeah.
Okay. And can I just ask a question?
Of course. Yeah.
I'm a little bit confused about the difference between Y star and Y.
So Y is the given data set that you have. say like in the exponential example, it's 10 observations of the waiting times, right? And Y star, we use it as a notation for a newly generated draw. So that's a prediction. Say now I have 10 observations now with varied varied number, and then I put an exponential distribution on it. I use a gamma prior to analyze this problem, and then I come to a posterior, right? Posterior with, yeah, posterior using Y, yeah. A Y star is a new waiting time that I can generate from the posterior distribution.
Okay, so like we're working backwards, we're getting the data from the posterior.
But Y star is new data, so not really backwards. You keep doing so. Okay, so you start with the data model, right? And you start, and then you come up with the prior, and then from there you go to a posterior. And now from the posterior, which is the gamma posterior for the beta values, I want to generate new waiting times out of it. So then we show that using Monte Carlo approximation, you can generate new betas first from the gamma posterior, and then from each of the beta, you're generating a new Y star. So the Y star is different from Y because this, like Y is the given data, a Y star is a new generated value. But they're trying to, but what we've been talking about so far today is to see, okay, like if you look at how the Y stars are behaving, it actually can tell you something about whether the model is doing a good job.
Okay. But when you say it produces a new beta from the posterior, so beta is like the theta in this case. So are you like, so you're creating a new prior?
No, sorry. Okay. So you start with the prior, combine with the data model, and then you go to a posterior. In this case, it's a gamma distribution.
Right.
It's given, right? We derived it. We know what it is. So when I say I make a draw out of it, I'm just using like R gamma over there. So like you can you know the beta posterior of the beta is a gamma distribution with the rate and shape that we know.
Right.
But right now we're using R gamma to generate random draws out of it. So we're not doing like a new distribution. We're just using multi-color approximation to the actual posterior distribution.
Okay. So that's going to be Y star, and then that's how we can use it to see if it's a good approximation, like to compare the means, which is what I did here.
Yeah. So if you want to know, say for example, this is probably the code, right? Yeah. So all of this, so the particular part that we talked about today is from here. Okay. Yeah. So right. So all of this, I mean, we talked about really quick in class, but all of this demonstrates exactly what we did in class. So I would suggest you like try to do it line by line if you want.
Okay. Thank you.
Yeah. And for the lab, you can work in pairs if you want, or eventually you should.
So this first one, looking at prior distribution, that's unspecified.
Oh, that's probably true. I thought I did. Okay, so it's a Poisson, so you're just gonna use the gamma. Okay, do you have a copy of the textbook? Maybe they used it, but I forgot to include it over here. Right, so here we have the data, like the data model, the data set. So it's 61, page 61. Okay, sorry. So maybe it's even before. So the example is from 3.2. Yeah, so it's over here. And let me quickly update it. Start with the gamma AB. Give me a second. They use both gamma 2.1. Yes, thank you. Right. Yeah. Good point. Yeah. So in order to verify exactly what they did, gamma 2.1 will be the one you use, but you can try with different things. But for now, maybe just 2.1. And I should make the note the whole class. Tony just asked a really good question. I realized in the lab 2 document that I put, I forgot to put the prior distribution. So sorry. So both theta 1 and theta 2 gonna follow gamma distribution with 2 and 1 as the parameters. So it's gamma 2, 1. Okay. Let me write it over here. So both theta 1 and theta 2 is gamma 2, 1. Okay, 2 parameters over here. Sorry about that. So in R, yeah, those will be the 2 will be the shape and 1 will be the rate. And I'll update the document on Moodle after class today.
We were making the one distribution of predictive values, or we're doing one example.
Oh, it's not about the predictive. Sorry, this is here for this particular exercise. Is doing predictions, not with like so many different samples. Yeah. Okay. Also, just just a comment for the lab. We're not doing the posterior predictive checks. Okay, you're just generating new data. Okay, not the last part that we talked about, but only the previous predictions. So if you notice, part A is asking you to do the multicolor approximation that I described. Okay, you generate a draw from the posterior distribution and then use the data model, you generate a new data point. Okay, part B, if you have read the textbook carefully, back in chapter 3, they actually provide you the exact distribution of the gamma Poisson model, which is a negative binomial distribution. So you can also, so part B is asking you to actually just use multicolor approximation from the true negative binomial distribution. Okay, and part C is asking you to verify if these two are the same. Okay, and this, I was hoping that this lab can serve as a verification of, okay, you can actually just break it into 2 steps. I'm going to generate draws from the posterior first and then use the data model, so I don't need to worry about what the exact posterior predictive distribution would be. Okay, yeah, once you've done it, maybe it's going to become clearer. But ask me any questions if you have, and then you can do it individually. You can also do it in pairs, and then in the end, I will put you all on Teams, and then this will be part of what you should talk about on Monday at the beginning, in addition to 3.3. Yes, Katie.
Okay, so I did part A, and I have like histograms. I mean, it's not super exciting. They look like that. But then for part B, so it's the same inputs. It's the same parameters.
Right. So
negative binomial.
Right. So maybe did you check the help file?
Yeah, it doesn't like it.
What did they say? The help file, did they say what is R by norm? So you need to just size probability. Okay. Let's see. Let me get a copy of the textbook just to read it carefully. Yeah, so the 2 parameters are exactly the same, right? So maybe it's just our problem at the moment, how we can fit, and then they don't give it to you, okay? So let me just check what I did, because I guess I figured it out before, but I don't remember it. Yeah, give me a second. Let me see what I had over here. But negative binomial does have 2 parameters, so I think. Okay. Yeah, so I should, okay. So for the negative binomial, like A and B, you should do, so R by norm, the first one will be the number of draws. The second one will be A over B, whatever you have. And then, so which will be the sum, I guess. And then the size will just be the A that you have. So what is your, so you have, oh, sorry, not A over B, sorry, the numbers that you have. So A over B, and then the size will just be A. Yeah. Right. I should also make that as a note. The last one is just A.
No, that's only 3.
No, just A. So you delete all of them. You don't need the rest. Sorry. Yeah. Yeah. No, it should be, let's see. Can you just put in A over there? I know, yeah, but can you run it really quick? Because I think I run. No, I got mu equals to, okay, I mean, I can just show you what I did. It's R by norm, R M by norm, and then 10,000, and mu is whatever sum, okay, A, so, no, it's two,
Oh, so
two,
you did 2 1
but, right, divided by, and then with the parentheses, yeah, and this size, what I have is, maybe, can you just also type mu equals to, so I think that's probably what it's problematic, and then size equals to 2 plus 272, yeah, yes, okay, good point, let me actually update that. Okay, one more really quick comment, because I guess I forgot to include this in the handout, in addition to the priors. So this one, so if you already made to point B, part B, you realize that, okay, we now know what the two parameters for the negative binomial is, but in R, they actually use a different parameterization. So just so you know, if you're generating negative binomial with A and B, then in R, you're going to use R and binom. And then here, this will be the number of draws that you're making. You need to tell R, you have to type as well, mu equals to A over B, plug in whatever values that you're working on. And you also need to tell R that size equals to A. Okay, it's just like it's just how like the function R and binorm was written. You need to fit in all of those values. So if you figure out that you're doing an MB, a negative binomial A and B, this will be what you fit in, and then that should be able to generate the draws that you want. Okay, so I again will go back and update that on the document and update it on Moodle. Yeah, thank you for the comment. And Brent, do you have any particular questions that I can help? Okay, yeah, great. Of course, yeah.
In this case, does that mean if I do it individually, S would be 111?
S is the total number of draws that you're doing, right?
So am I going to do the same number of draws?
Oh, for all of them? Let's see. So this is telling you that the sample size for the first one is 111, right?
Yeah.
But for A, it's just okay. So for A, it's asking you to generate new data points. So you know that it's gamma 219 and 112, right? So that will be good enough. So this is just the sample size.
Right.
But if you're only generating new draws, you don't have to match the sample size. So what we're talking about matching the sample size is when you're doing posterior predictive checks, because now you want to do all of them in the same size. Oh, no, okay. Yeah, so here it's just like sample, and then, yeah, so first of all, you're going to generate one theta, right, from the posterior. That's what you do, one, but you can do it for 10,000, you can do it together. So so this beta contains the vector, right, of 10,000 independent draws of theta, right? And then from each of that, you're doing a new y, which is what you did over here. However, it's not R EXP, because here is a Poisson model. Yeah.
Okay.
So this, right. So this, not in this exercise, but this is related to the posterior predictive checks. So can I show you on the sample code that I had? Yeah. So you see that over here, this is what I'm doing. So if you're doing posterior predictive model checking, you set an S out there, and then every time you want to generate a new data set has the same number of observations as before. And that's where you can match, in this case, my 10 will be 111 over there. But this is not what the question is asking. But good good to start thinking about it because at some point you might need to use it, right?
But then here, so this, just to make sure I understand.
Yeah.
Right. So this was the data
Yeah.
that we got.
Yeah.
But here, we just have the sum.
You don't even need it. Yeah. Yeah. So that's why only if you're doing with the posterior predictive checking, you should know exactly what the original data is, because if I want to get the mean, the variance, I need the original data, right? Here is not. Here is you're just doing new predictions based on the posterior that you can derive already. So you only need those summary statistics. I tell you everything already, so you don't need to have the access to the original data. No, not this one. But no, don't worry. Mostly just over here. This 4 lines is what you can do for this part. Okay. Yeah. All right. Okay. Let me just end it here. Thank you, Grant. Yeah.